Good morning, ma'am. Am I audible? Am I audible? Anyone please respond? Students, am I audible?
Yes, ma'am.
If you have any WhatsApp group, ask your friends to join. Okay, what are the topics that we have discussed in the previous class? Do you remember those topics? At least the names of those topics. We were discussing about transport layer, the protocol supported in transport layer, right? What are the two main protocols? TCP and UDP. We will not be concentrating on SCTP. So we'll be seeing reliability. We have seen reliability, how reliability is supported in TCP, how flow control is supported on TCP using congestion, that is sliding windows, congestion control solutions, that is leaky bucket algorithm, and also token bucket algorithm, which comes under open loop congestion control solutions. And also we've seen closed loop congestion control solutions. And we have started with congestion control that with the help of sliding window protocols like slow start, AIMT, that is additive increase, multiplicative decrease. Okay, how TCP will be reacting, starting from there will be three stages, right? So slow start, it enters into additive increase. Then if there is a congestion detected, it comes to multiplicative decrease, right? So those things we have seen in the previous class. We'll continue with the TCP congestion control, different variants. Okay, before that, I'll share my screen. Whether my screen is visible?
Yes, ma'am.
Thank you.
Yes, sir.
This class, we'll see TCP congestion control variants, different variants like SAC, TCP Vegas, and Compton TCP. Okay. So how high speed TCP variants, that is TCP and high speed TCP, providing high speed. That also we'll see in this class, right? Just a second. I'll start with TCP Tahoe. Okay. So TCP Tahoe, starting one is slow start. Okay. It is an early congestion control mechanism. So early congestion control mechanisms, in the sense it will be designed to avoid the network congestion. And also in order to ensure efficient data transmission, TCP Tahoe is designed. Okay. So three phases are there. It works in three phases. It starts with slow start. It enters into congestion avoidance, and it comes back to the fast retransfer. Okay. So the first one is slow start. Okay. A very small congestion window. I'll take always the congestion window starts with one. Okay. So this will be for each and every acknowledgement that it receives, it will be doubling the size of the congestion window. Okay. So exponential growth will be there. Okay. So it congestion window starts with one and it grows exponentially until it reaches certain threshold. Once it reaches the threshold, it enters into congestion avoidance state where the congestion window will be additively increased. Okay. So once there is a congestion detected, okay, so immediately it enters into fast retransfer. Okay. So rapid growth allows the TCP to utilize the available bandwidth. So this continues till the congestion window reaches the threshold. Okay. So once the packet loss, and then it will be entering into additive increase state once the threshold is reached. So until the packet loss is detected, it will be entering into, it will be there in additive increase. So once the congestion window reaches the threshold, it switches from the slow start state to congestion avoidance state. Okay, there will be a linear growth from the exponential growth. It enters into a linear growth. Okay, so the congestion window will increases uh, uh, by with the value of 1. Okay, gradual increase. Okay, so available bandwidth will be utilized properly without overloading the network. Okay, so it will be reducing the risk of the congestion. Okay, so if any of the packet loss is detected, or is if any time of is happening, or if I'm getting any three duplicate acknowledgements, so Tahoe will be reacting in such a way that so it will set whatever the threshold. So if my threshold size is threshold value is 8. Okay. And I've reached the threshold. My current congestion window size is 12. So it will set the threshold value to half of the current window. What's the half of the current window size is 12? Half of the current window size will be set to threshold value. And also it will come to the, again, it comes to the slow start state. Okay. Instead of coming to the slow start state, it will be setting the threshold value to half the current size, and also this value will be set for the threshold, current threshold, and it enters into additive increase. Fine. So the congestion window, it will reset, and then once it reaches, obviously the congestion, say for example, it is starting from the slow start. Okay, so this is my threshold. Additive increase is happening. There is a three duplicate acknowledgement is received. Okay, so half of the size will be set. Okay, so this the current window size will be, if I'm taking it as 12, now the window size becomes 6, and also the threshold value also becomes 6. Okay, then it enters into, again, it will be entering into additive increase. Okay, so it's slowly building up, it will slowly starts to build up the transmission rate again. So if through duplicate acknowledgements are received, okay, so Toho will be retransmit the lost packet immediately without waiting for the retransmission time. Okay, but Renault will not do that, but even the turbo will be resetting the value. The congestion window will be set to the half the current size, and also it enters into additive increase. But it will partially retransmit. Okay, so TCP Tahoe follows a repeated cycle, exponential growth during slow start, linear growth during congestion avoidance, and it will come to the reduction uh, once the packet loss is happening. Okay, but it will not enter into slow start. Again, it comes to additive increase. Fine. Any doubts? Do you have any doubts? Any doubts?
No, ma'am.
So the next one is Renault. Renault starts with slow start, congestion avoidance, fast retransmit, and recovery. Okay, so TCP Renault, it is an enhanced over TCP Java. Okay, so it is designed to improve the congestion control, and also together with that, it will be maintaining the higher throughput. Okay, so even after the packet loss. So it uses for it will be using four main mechanisms. The first one is slow start, congestion avoidance, then fast retransmit, and the fourth one is fast recovery. Okay, so it is similar to Tahoe. The Renault will start from the congestion slow start by setting the congestion window size to 1. Okay, so one segment size, the window size will be set to 1. So window will be growing exponentially. So this is the value. So it is growing exponentially. As you can see here, it is 2, 4, 8, 16. For each and every acknowledgement it is receiving, the condition window size is doubled. Okay, so it is an exponential growth. So window grows exponentially with the acknowledgement. So doubling each For every round trip time, it is doubling the window size. Okay, so this will get continued. So now it is reaching the threshold value. In this example, the threshold value is 32. Okay, so once it reaches the threshold value, what will happen? It enters into, this is slow start state, and this is congestion avoidance state. So this entire phase is slow start. This is congestion avoidance, where the Renault will be switching it to a linear growth rather than an exponential growth. This is exponential growth. Okay. So this one will be the linear growth. Fine. So the congestion window will be increasing by one for each and every packet acknowledgement it gets received. The congestion window will be added with one. From 32, it becomes 33. Then it becomes 34. Now it becomes 35. Okay. So this will be avoiding overwhelming the network. Okay. It still increases the throughput gradually, but it will avoid overwhelming the network. Okay. I've not put much amount of data. So when here in this stage, it receives when through three duplicate acknowledgements are received. So what the Renault will do? So Renault will perform fast retransmit. Here it will perform fast retransmit of the last packets. Immediately it will be sending all the last packets. Okay, for by seeing the duplicate, it will be sending the packets immediately. Okay, it will not wait for the long timeout. Okay, so Renault does not reset the congestion window size to 1 MSS. So instead, what will happen? It will enter into fast recovery. So this is the fast recovery state. Okay, so the threshold value will be set to the current half the size of the window size. Okay, so I think it is 42. It becomes 21. Okay, so the Renault will continue transferring new packets. Okay, as a duplicate acknowledgements. So even when it is getting a duplicate acknowledgements arrive, it will be maintaining the throughput. So once an acknowledgement for all the retransmitted packet is received, the Renault will exit from the fast recovery. Again, it will be transmitting, transitions will be done based upon the congestion avoidance. Okay, so when multiple packet loss occurs within the window size, obviously it will be failing to receive enough duplicate acknowledgements. So it leads to timeout. In that case, renewable again it falls to slow start, say, by setting the condition window size to 1. Okay, this also happens. So in okay, the difference between TCP renewal and TCP toggle is immediately it starts the function. This is the slow start state. Okay, so it will be setting the condition window size to 1. Okay, so slow start state, exponential growth will happen. Okay, so until it reaches the threshold value, both are same. Fine. Congestion avoidance state by adding the congestion window exactly by 1. Okay, so it is a linear growth. Here also, both are same. There is no difference. Okay, the difference comes in three duplicate acknowledgements. So if three duplicate acknowledgements are arriving, so in that case, what will happen? So here, the congestion window size will be set to 1 at enters into slow start. But in this case, Renault, it will not set the congestion window size to 1. Instead, the current window size, congestion window size divided by 2 will be set to window size and the threshold value. Okay. So if further timeout is happening, then only the condition window will be set to 1 and it will be entering into slow starts. Okay. That is the difference between TCP Tahoe and TCP Ready. Fine. The next one is TCP SAC. So selective acknowledgements. SAC is nothing but selective acknowledgements. Selective acknowledgement and fast recovery. Okay. So it is an improvement, improvised version over the TCP Reno and TCP Tahoe. Okay. So which will be handling multiple packet losses in an efficient way. So it allows the receiver to acknowledge even the non-continuous block of packets that selective repeat. Okay. So in that way, it will be improving the performance in even in the lossy network. Okay. So traditional cumulative acknowledgements will be received. So the receiver can only acknowledge the highest in order bucket received. Already we have seen in TCP selective repeat, right? So SAC can acknowledge separate as well as non-continuous blocks of data. So for example, it can send acknowledgements like SAC0, who's SAC 1023, and acknowledgement like the numbers 1024 to 2047. So even some segments in between are missing. This helps the sender identify which segment have been received successfully. Okay. So another important point in SAP is that multiple SAP blocks can be included in a single segment, so that it allows the receiver to communicate the status of multiple out of order segments without waiting for cumulative acknowledgement. Okay. So TCP SAP, it will be entering into fast retransmit when it receives any three duplicate acknowledgements. So it is similar to REN, but the sender will be using the SAC information for maintaining an accurate uh, the data of which segment have been received or which are missing. All those things can be identified with the help of an acknowledgement. So this will enable the sender for retransmitting only the lost packets. Instead of retransmitting the entire window of the data, it will, whatever the packets that are being missing, only those packets will be sent. Okay, so this was the limitation in Reno that is rectified in uh, TCP SAC. Okay, so the sender will keep track of all the SAC segments, and this will be used to find which segments are missing or outstanding. Okay, so from that, it can retransmit the segments, or else further it can transfer another segment. So it improves the performance. Okay, so TCP SAC is nothing but a selective acknowledgement mechanism. So it can able to handle multiple packet losses, even there are missing packets in between. Say, for example, I'm sending this is sender and receiver. So I'm sending the segments from 1 to 1000. Okay. So segment number, sequence number, I'll say it is 0. For the next one, I'm saying sequence number as 1000. The next number, sequence number is 2000. And the 3000 is missed. The next number, sequence number is 4000. What does it mean? 0 to 999 is received, 1000 to 1999 is received, and 2000 to 2999 is received. So what will be the acknowledgement for this packet? ACK 1000. Tells I'm waiting AC next byte. So ACK 2000. For this, what will be the acknowledgement? ACK 3000. So what happened here? There is a packet loss, right? So this will not be received at the receiving side. Okay, so after this packet is received, it will be telling ACK 3000. Okay, so in particular, how SAC will be transmitted? SAC 0 to 999, SAC 1000 to 1999, selective acknowledgement 2000 to 2999. Okay, again, SAC 4000 to 4999. So this packet is missing. The sender can identify which bytes are still missing. So it enters into fast retransmit, and it will be soon after it receiving the acknowledgement, it will be sending that packet alone. You understand? Any doubts? Any doubts, ma'am? Do you have any doubts? The fast recovery, that also with pipeline mechanics. Okay, so TCP, selective acknowledgement, it will handle multiple packet losses with the help of selective retransmission. Okay, so in addition to acknowledging non-continuous block of data, SAC will also introduce a fast recovery mechanism, which is called as pipe algorithm. Okay, so whenever the sender enters into fast recovery, it will be initializing the variable, which is called as pipe. Okay, so this variable, it is an estimation of how much data that is currently outstanding in the network. Okay, so it means the data that has been sent but not yet acknowledged, that will be there in the pipe. So this pipe will be dynamically updated. So every time the sender receives an acknowledgement, this value will be either decreased or increased by indicating what are the outstanding still, how many packets are still outstanding. Okay, so every time the sender retransmitting a lost segment, the pipe will be incremented by one. So it assumes there is no more outstanding segment in transmit. So the sender will be using the pipe to decide when to send more data. Okay, so whenever the pipe becomes smaller, the congestion window. So if I'm checking with the congestion window size, so pipe is smaller than the congestion window size. So there is an available capacity in the network. So in that case, the sender can increase the congestion window size. It can send multiple number of packets at the same. Okay, so the sender will be checking which segments have not been received by the receiver. So based upon the SAC information, it will be retransmitting those packets. So once all the outstanding packets are there, sent the SAC with the help of acknowledged SAC acknowledgements, the fast recovery. It enters into congestion avoidance and it will be growing the window size gradually. So if there are no outstanding packets, lost segments or retransmitting is there. So the receiver has acknowledged everything. In that case, the sender will be sending the new packets. So this pipe-based mechanism can combine selective acknowledgement blocks, and also it allows TCP SAC to estimate the amount of the data or how much data uh, still are outstanding, and it can recover much faster from multiple packet losses when compared to Tahoe and Renault. So it uses this pipe for estimating those informations, right? So the next one is TCP congestion strategy. So from control to avoidance. So the fundamental objective is to manage the network congestion. Okay, so even that we have to maintain efficient data transmission. Okay, so TCP, it follows a congestion control strategy, but it also newer approaches are still evolving towards congestion avoidance. Okay, so how the classic TCP works based upon what strategy it is used. So this strategy it is used in variants like Tahoe, Renault, congestion control, congestion, how the congestion control happens. Okay, so the sender will be increasing the transmission rate. Okay. So it will be probing the network capacity. So until the congestion occurs. So whenever the congestion is occurred, once the packet loss or else either the packet loss or the three duplicate acknowledgements, it indicates the congestion. So what the TCP will do, TCP will reduce the sending rate, and also it goes into back off phase. So this reactive method, it works very well, but it leads to packet drops before any action is taken. So definitely it will waste the bandwidth. So there is an improved alternative mechanism which focuses on congestion avoidance. We can predict and we can prevent congestion before it has happened. So instead of waiting for a packet loss, these methods will detect early signs of congestion and then it will be reducing the sending rate. Okay, so that happens proactively. So it will be preventing the buffer overflow and also the packet drops. Okay, So this is why it is referred as congestion avoidance instead of congestion control. Okay, so there are two main approaches for that, for the congestion avoidance. The first one is host-centric approach, okay, which is used by TCP Vegas. TCP Vegas will be predicting the congestion by monitoring RTT, round trip time. So this RTT, if it increases, it indicates the queue sizes are growing in the network. So in the meanwhile, what will happen? The Vegas will reduce the sending rate. Okay, before the packet loss is happening. So by seeing the RTT itself, it identifies we are making further load on the buffers and the routers. So buffer size is running out. So meanwhile, it will be reducing the sending rate. So this way, the congestion avoidance is happening in TCP waivers. The next one is with the help of router centric. The router centric, we have discussed two things. It is DEC bit. Okay, so DEC bit, it is a single congestion control bit which will be there in the router headers. Okay, so the average queue length, if it is exceeding the queue size, this is my router buffer. So this is my capacity. So this is my threshold size of the buffer. Okay, buffers threshold. So if this threshold value exceeds, what will happen? So once it reaches the threshold value, so whenever the packet comes in, all the packets in the header, the DEC bit will be set. Okay, so it will be sent to the receiver. The receiver will be copying that bit in the ACK. So this bit will be set to 1. Okay. Then it will be informed to the sender. Fine. So the sender will be adjusting the rate based upon the feedback. Okay. So when it passes to the router, so the router's threshold buffer size threshold value is reached, this bit will be set in the incoming packet. The receiver will be copying that bit in the acknowledgement, then it will be transmitted to the sender. So sender, meanwhile, it will be reducing the congestion, sorry, sending rate. Okay, the next one is RED, random early detection gateways. Okay, so it will be waiting, it will be monitoring the average queue size. So randomly drop, it will try to drop the packets before the queue overflows. Okay, so when I'm dropping the packet, what will happen? So the router is dropping some of the packets. So timeout happens, right? So if further timeout is happening, the TCP definitely it will assume there is a condition. So it is an early condition signal to the sender. So to prompt the sender to slow down the transmission. Okay. So this is how the TCP variants like Tahoe, Reno, Vegas, and also DC bit, RED. It has help us to help the network to reduce the congestion with the help of congestion detection or congestion avoidance. Vegas, TCP, Tahoe, Reno, those are congestion detection. Once the congestion is happening, it will be overcoming. It will come out of the congestion. The next two things are congestion avoidance. Three are congestion avoidance. Once the congestion is happened, sorry, before the congestion is happening, what are the mechanisms to come out from the congestion? Okay, any doubts now? Do you have any doubts? What are the others? I'm there in the meeting. Now we'll see TCP papers. So early condition detection with the help of RTT, right? So it is an incremental bar compared to TCP Reno and TCP tower because it will detect the congestion before it is happening. Okay, before the packet loss occurs, it will be detecting the condition. So instead of say waiting for the three duplicate acknowledgements or time modes, Vegas will be using another value that is RTT round trip time for indicating that will be used to indicate whether there is any congestion is happened or not. Okay. So TCP Vegas is a congestion avoidance. Okay. So the queue length in the network will begin to get increased. And also RTT, even the RTT will be increasing, right? So once the RTT, the big, so I'm sending the packets, the router. Okay. So router will be getting multiple packets from different senders, right? So the queue becomes, here there is a queue becomes full. What happened? So RTT will increase, right? The time to send the packet and get an acknowledgement. This will increase. Why? Because the waiting time in the queue, the waiting time increases, the say by RTT increases, right? This will be informed to sender. So sender proactively, what it will do is it will say adjust the sending rate. Okay, so it will prevent the condition before it is started. Okay, this is what it is different from Tahoe and Renault. Okay, so which is Tahoe and Renault will be reacting only after the packet loss, but here uh, it will not wait for the packet loss. Instead, what will happen? By seeing the RTT, it will be adjusting the rate. So Vega's algorithm, it is based upon base RTT value. Okay, so base RTT, it is nothing but which is defined as the minimum of the measured RTTs. That will be our base RTT. Okay, so the RTT, the very first packet which is being sent, that value will be taken, and the propagation delay with no queuing delay that will be taken. That will be set to the base RTT. Okay, so the first packet I'm sent and the acknowledgement received. Okay, there will not be any queue in the network. So there will not be any waiting time in the router. Why? Because the queue is empty. So there is no propagation delay, there is no queuing delay. So that time will be set to the RTT. So Vegas will be calculating the expected transmission rate using the formula expected rate equal to congestion window divided by base RTT. So once for RTT, the Vegas will be calculating the sending rate. So it will calculate sending rate based upon the data acknowledged during the interval. Okay. So then it will compare it with the actual rate, with the expected rate. Okay. So what is the actual rate and what is the expected rate? That the difference between these two will be taken. Okay. So which is stored inside DIFF. That is the difference. How the congestion window can be adjusted. Okay, what is the expected rate? What is the actual rate? What is the difference? That will be made there. So if it is smaller, okay, so A is a threshold value. Here A is a threshold value. Okay, if it is smaller than a lower threshold value, A is a lower threshold value. Okay, and B is a higher threshold value. Okay, it will check with whether the difference is less than A. Fine. So if it is less than A, lower threshold value, the network here it is underutilized. Okay, the network is underutilized, so the Vegas can increase the congestion window. So it will increase the congestion window linearly. Okay, but if the difference is upper threshold value, okay, so it is a lower threshold value, and this one is a upper threshold value. So if it is greater than the upper threshold value, what does it mean? There is a possibility of the congestion. So here it will decrease the congestion window linearly. So here there is a possibility of there is no congestion, so I can increase. So if the threshold value, if it is greater than the upper threshold value, it will be decreasing the congestion window. So if the difference between these two thresholds that will be taken care. Based upon that, the congestion windows will be taken. So if both are same, nothing will happen. It will leave the congestion window unchanged. Okay, so the network will operate in an optimized way. So this is the proactive adjustment. So with the help of that RTT, the expected rate, the Vegas will try to stable the throughput and it will avoid the congestion. Okay, any doubts? Any doubts?
No, ma'am.
Now we'll see the difference between TCP Reno and TCP Vegas. Okay, the comparison between the congestion window behavior of TCP Reno and TCP Vegas over time. So the red line, it indicates TCP red. So the green line, it indicates TCP Vegas. So Renault, it follows the loss-based congestion control, right? It starts with low start, exponential growth, linear growth. It reduces the congestion window, half the window. Again, it goes linear. The three duplicate acknowledgements, half the size. Again, linear growth. This is TCP Renault. Okay, so continuously it increases the congestion window until the packet loss is happening. So when the loss is detected, the window size is divided, the half of the window size is taken, and again it goes into linear increase, right? Whereas, as you can see here, Vegas, it is delay-based approach. Okay, so based upon the delay, it gets decreased, increased, decreased, increased. Okay, the Vegas will be detecting early signs of the congestion. Okay, by monitoring the RBT value. So thereby it will try to adjust the sending rate before the packet losses happen. So instead of waiting for a packet drop, it will the Vegas will stabilize the condition window around the operating point. Okay, so that's the reason the oscillations is happening there. Right? So the next one is compound TCP. The compound TCP balancing in order to balance the efficiency and fairness. The C3 is a congestion control algorithm which was developed by Microsoft. Okay, it is a part of Windows Vista and also Windows Server 2008 TCP stack. So objective to improve the Windows. Who was that? Any doubts? Okay. The compound TCP, right? So compound TCP, it tries to fully utilize the bandwidth. Okay, so it will be adjusting the sentence window size, and also it will try to utilize the bandwidth in a optimized way. Okay, that too in an effective way. Okay, so well suited for networks where the traditional TCP variants like Renault it is not, Renault will be underutilizing the bandwidth, right? Due to loss-based approach, right? So that's the reason compound TCP is built. Okay, instead of waiting for the packet loss or getting a three duplicate acknowledgements, it considers the variation in RTT, that is round trip time. So it increases, increasing RTTs. What does it indicate? The growing queues. Okay, and there is a possibility of the congestion. So if my RTT is growing, or sorry, if my RTT is increasing, so it indicates the queue size is getting increased, and the have to wait for a longer time. So there is a possibility of congestion. So when RTT variations are there, so then reduce CTCP proactively. It will try to reduce the sending rate before the packet loss is happening. So this is how it efficiently stables the congestion rate and also improves the better performance in the network. It gives the better performance in the network. So in networks, their competing flows they are loss based. Okay, so like such as Renault, the CTCP bandwidth, it will try to unpair the bandwidth sharing. So it attempts to optimize the high speed performance. Okay, so underutilized based upon underutilization, like how TCP handles depending upon how other flows behave. So based upon that, the CTCP it overcomes this. So compound TCP it is designed to provide high speed, to work on high speed networks. So by combining the bandwidth utilization and also together with the RTT based condition detection. So for that, large bandwidth delay products, so high in order to provide higher fairness. For that, in order to achieve a balance between efficiency and fairness. Okay, so especially the traditional loss-based TCP variants are uh, not working well. In that case, we can go for compound TCP. So it is a scalable delay-based component. It enhances traditional TCP by combining both loss-based and also the delay-based. Okay. So condition control components, we'll be concentrating both on loss-based and delay-based. Okay. So it makes it suitable for high speed and also large bandwidth delay product networks. Right. So we'll see the unique feature of CTCP. It maintains two separate windows. One is condition window and the next one is delay-based window. So condition window, it is handling the loss base in order to handle the loss-based congestion control. So this is the delay-based window. So it will adjust based upon the sending rate. Okay, sending rate will be adjusted based upon the RTT variations. Right. So whichever is minimum, that will be taken for the window size. So the effective window size will be calculated like minimum of, so advertised window. So this is the advertised window and condition window plus the delay based window. This will be added together. And if it is less than the advertised window, that will be taken, or else this is too larger in compared to advertised window. So in that case, advertised window will be taken. So it ensures sender does not exceed the receiver's buffer capacity. Okay, so during the slow start phase, the TCP it initializes the delay based window size to 0. Okay. So the standard loss-based TCP to maintain the compatibility, that's the reason a delay-based window will be initialized to 0. Okay, so it will stabilize the connection. So the delay-based window, it will increase based upon the network delay feedback. So so that it tries to utilize the available bandwidth when there is no condition. In that case, gradually it will be increased. Okay. The congestion window, it continues to work like a loss-based component. So it reduces the sending rate when the packet loss occurs, okay, by saying the RTT. And also the delay-based window will be adjusted to prevent the condition by reacting to the RTT variations. Okay, so this both the window will be designed so that the aggressive, the traditional TCP, uh, wherever it fails, it still tries to remain there by backing off when the condition signal appears. So TCP intelligently it will be blending both the things, that is loss-based components together with the delay-based components. Okay, using two windows, condition window and delay-based window for the early detection, condition detection. Okay, so and also early condition. This is for early condition detection, and this is for early congestion avoidance. Right? Any doubts? No, we see high-speed TCP variants. So it is needed for advanced congestion control. Okay. So high-speed networks, the traditional TCP variants, like whatever that we have discussed when that over, they'll become inefficient for the modern applications, right? Newer applications, being telemedicine, real-time environmental monitoring. So demand will be having a greater performance. Will not be provided by the conventional TCP. Okay. So conventional, that is classical TCP will not provide all those things. So newer applications, right, wherever the real-time environment monitoring, telemedicine. So these applications will involve transmissions of large volumes of high bandwidth, that is real-time data. So medical image systems, okay, satellite-based remote sensing, radar systems, all these things will be generating massive data. Okay, so all those things will be transferred in a quicker way and also in a reliable way across the geographically distributed networks. So the requirements for these applications will be going beyond just higher bandwidth. So they require a predictable, low latency data transfer that will with a minimum jitter. Okay, so small delays or packet losses will disturb the entire network, the real-time operations, right? So telemedicine, if I'm taking telemedicine, high resolution video feeds are required, surgical equipments, diagnostic tools. So all these things must be transmitted without any interruptions, right? So environment monitoring using remote sensors, all these requires a reliable uh, data delivery for making timely decisions. So traditional TCPs failure, so they rely on a packet loss as a congestion signal. So it will not be giving higher speed. So they cannot fully utilize their bandwidth and the performance will happen sometime. So in order to address all these challenges, high-speed TCP variants so that are being developed. Okay, so this will modify the congestion control algorithm so that they can uh, scale efficiently, that too with a larger bandwidth delay products. So it will give the better performance, okay, better throughput, and also it maintains the fairness and stability. Okay, so it will maintain strict requirements of modern data sensitive real-time applications. So in a faster and more predictable way. Right? So now we'll see high-speed TCP, the different high-speed TCP variants, the challenges in high-speed, higher bandwidth delay networks. So traditional TCP congestion control mechanisms, they face certain challenges in high-speed, high bandwidth delay product networks, right? So the TCP, it increases its condition window by one for RTT. right? So one per RTT. And also it reduces the half of the window size when the loss packet loss is happening, right? So this growth, it will limit the performance on high capacity needs. So say for example, in order to fully utilize a 10 Gbps link with 1500 bytes packet, TCP approximately it needs 83,333 RTT to reach the full utilization. So if RTT is around 100 milliseconds, okay, we'll take it is around 100 milliseconds. Okay, it is 1.5 hours. Okay, it will take nearly 1.5 hours for the modern real-time applications, right? So the key challenges will arise in designing high-speed TCP VPNs. So for sending this data for 1.4 hours, that is too much, right? So we should simplify or how the MSS increase the MSS size. So the larger MSS will help us in uh, sending the data much in a faster way. So the fragmentation issues, compatibility problems, all these things exist in the network infrastructure. So we have to give the fairness with standard TCP flows. So any high-speed TCP variants, they must coexist fairly with traditional TCP implements. So it cannot dominate bandwidth to a certain extent. Okay, so it should be aggressive enough to utilize the full bandwidth capacity. And also it should avoid congestion, right? High speed variants. It should balance the aggressive window growth. So too much aggressive, again, it leads to congestion. That also has to be avoided. So the pipe, so need to fill the pipe quickly and also fairly in higher bandwidth delay environments. So high speed delay variant. It should scale congestion window rapidly to match the available bandwidth. Okay, and also it should react to the congestion signals even. Okay, so high speed TCP variants, uh, all these things has to be overcome. So in order to overcome the inefficiencies that are faced in traditional TCP, they must be scalable. It should be giving the fairness, and also it should provide congestion aware for supporting modern applications. So for scientific data transfers, telemedicine, real-time environments, monitoring. Okay, high-speed TCP variants will support all these things, right? Any doubts? Any doubts? Do you have any doubts? How many times have you asked? Okay. Now we'll see the solutions. Okay. High-speed TCP variants. Solutions for efficient data transfer. Fine. To overcome the limitations of traditional TCP, in high speed, high bandwidth delay products, we can have several strategies. So several strategies are proposed. And the first approach is fine tuning. So fine tuning TCP parameters. Fine. So what are the parameters? So we have to adjust the window size, the receiver window size, and also we have to increase the network interface buffer capacity. Okay, so this can help to utilize higher bandwidth. Another method, increase the packet size. Okay, so using the jumbo packet option, so which allows up to 8 KB. Okay, and also we have to reduce the number of acknowledgements required. Fine. Together with that, you can use multiple parallel TCP connections. This also helps to improve the throughput and high capacity networks. So these methods, uh, all these things, fine-tuning TCP parameters by increasing the packet size alone, they are not sufficient. So traditional TCP variant they have to use fixed increase rate for congestion window growth, right? So this will makes it difficult to balance the TCP friendliness or the fairness towards the standard TCP flows and also the bandwidth capacity. Okay, so the real solution by providing adaptive congestion control schemes. Okay, so they can adjust the window size, window growth rate based upon the network conditions. So it can enable both high bandwidth utilization. Together with that, it can give the fairness. Okay, so the first one is cubic TCP. So cubic TCP, it uses cubic window growth. Okay, so the window size will be increasing rapidly. Okay, so until the congestion is happening, right? So that it improves the stability and also fairness. The next one, high speed TCP. So it modifies the window and also it reduces the parameters based upon the window size, current window size. Okay, so aggressive increase will happen at higher in order to provide the higher speeds. So and also it will more likely to behave like a standard TCP. During the low rates, it will be behaving like a standard TCP. And if the network is not congested and the network is not loaded, in that case, it will be working like a high speed TCP. And the third one is multi-path TCP. So it uses multiple paths. As the name implies, it uses multiple paths simultaneously. Okay. So the bandwidth can be aggregated from different network interfaces. So by that, it will be providing higher throughput. So higher throughput, definitely it will take you to better reliability. So these schemes uh, will be providing adaptive high-speed TCP. So these can be designed to scale the network capacity to utilize the bandwidth in a optimized way and also in a reliable way. So even it will be providing the fairness will be retained. Okay, so based upon the traditional TCP flows, the fairness will be retained. So it will be either suited for both high-speed applications and also low-speed applications. When the network is congested, it will be working like a traditional TCP. If the network is not overloaded, it will be behaving like a high-speed TCP behavior. Fine. The three things in detail. The first one is cubic TCP. So cubic TCP, it is a scalable high-speed condition control. It is the most widely used high-speed TCP. Okay, that too, it is suited for Linux-based systems, right? Especially it is suited for Linux-based systems, uh, designed for networks with a larger, in order to support a large bandwidth delayed cortex. Okay, so the objective uh, to maintain or in order to make the window size grow in a cubic function of time. Okay, so based upon the condition window size will be growing in a cubic scalable. Okay, and also it will be predictable and efficient for a high speed networks. Okay, so the cubic function will be set to the condition window size. Okay, so based upon the after the condition signal is happened, the cubic modifies the growth. So it behaves in a two growth phase. It will have two phases. One is called as concave growth phase. Another one is called as convex growth phase. First, we'll see concave growth phase. So it will reduce the window. Immediately after reducing the window, the cubic uh, will quickly regain the previous window size. That is concave. Okay, so ramp up will happen here. So in order to ensure the network link is quickly filled again. after a lost event. It behaves in a concave growth phase. So after reducing the window size, okay, it will quickly regain the previous window size based upon the networking. Then next one is convex. Convex, once the window size reaches the congestion or threshold value or the previous congestion point, the cubic window will slow down the bandwidth. Okay, so the growth will be very low. So the network can be stabilized. The it will avoid the packet loss. Okay, so if there is no congestion is detected, so in that case, the cubic can again go to the explore exponential growth, the cubic rate. Okay, so the advantage is that it will switch between these two phases, convex and concave. Okay, a long steady period will be there so that the network queue can be stabilized and also it will be giving the better performance. Fine. So the cubic TCP achieves high stability and also bandwidth utilization will be very low, sorry, very high, and also it maintains the fairness. So cubic growth pattern will, in a fast recovery, it will grow in a cubic growth pattern. So if the congestion is broke, it will come to the convex. Convex, and the first one is convex, the next one is concave. Okay, slow down. It is gradually. So here it is convex. Grows convex is nothing but it grows, right? So the window size reaches here. This is my value where the congestion is there. So I can say this is a cubic point. Okay. So until this point, the window size will be growing in a cubic way. So and once it reaches the point, so it slows down and also uh, it decreases the condition window size. Okay. So for stabilizing, it will reduce the size. Okay. The condition window size will be retained or maintained to avoid the packet loss. Okay. So if no congestion is detected, so see here. So till this time, it retains the same window size. If no congestion is detected, it is going to the next phase. Okay, it increases the transmission. Right? Any doubts? Do you have any doubts? So high speed TCP, it is designed to overcome the limitation of standard TCP. That too for providing the higher bandwidth, that too in the high delay networks. Okay. So traditional TCP, it increases its congestion window. That too, it will increase the congestion window very slowly, right? So it will be inefficient for fully utilizing high speed links. Okay. So high TCP, it will be modifying this behavior to become more aggressive, right? So one day, it will be aggressive that too in a it will be aggressive that too in a specific conditions. Okay. So we'll see it becomes aggressive in a certain points where there is no competing with a large amount of standard TCP. There is no other flow. Okay. So much number of flows is not there in the network. My router is free. So it ensures the fairness is retained even when sharing the bandwidth the other conventional TCP flows. Fine. So my network is free. In that case, it will be aggressive, more aggressive. Okay. So if the network is fully loaded, it will work as a standard TCP. Okay. So it will support a large congestion window size, high speed links. So if my network is congested, in that case, it will be working as a normal TCP. So in normal operating environment, the TCP will be acting like a standard TCP. So when the congestion window is small, that is 4 times the maximum segment size. So if it is below the 40 times the maximum window size, there is no difference between the higher high-speed TCP and standard TCP, right? So the major change occurs when the congestion window becomes very large. Okay, so if it is very large, the high-speed TCP, it will start to increase the congestion window size. Okay, so that too in an aggressive way when compared to the standard TCP. Okay, it will try to utilize the all available high-speed bandwidth in an effective way. So this is how high-speed TCP will be maintaining the backward compatibility that too uh, like a standard TCP, and it will be providing fairness when it works with the other flows in the network. Okay, so if my network is not utilized properly, the congestion window size will be aggressively grows. So when my network is congested, it will be behave like a standard TCP. So there are three parameters. So now we'll see how it fine tunes the congestion window size. Okay, so based upon the response function. Okay, so it is designed for high speed, high bandwidth, high delay networks. Okay, so there is a response function which will be controlled by three parameters. Okay, so first one is low window, high window, and high peak. So the low window, this parameter will be representing the transmission point. So where the switch from the standard TCP to the high speed TCP until the window size reaches low window, this will happen. Okay, so the standard TCP behavior will be there to ensure fairness and compatibility with the traditional course. The next one is high window. High window, this parameter will be representing the target average congestion window size. Okay, to achieve high speed networks, in order to achieve in high speed networks, right? So this will be defining the upper end of the high TCP net, what is the upper end, upper operating point that can be utilizing the bandwidth in an effective way. Okay, what can be the maximum bandwidth? That will be your high peak. The next one is high peak. High peak is a drop probability. So drop probability, this is required for the response function in order to maintain the high window as the average condition window. Okay, so it will be adjusting this value so that the window size can be switched between the low window and high window. So it can be adjusted based upon this value. Okay, so the TCP, it starts with a standard, it starts like a standard TCP, high, okay, high speed TCP. It starts like a standard TCP. Okay, so until the network path, everything, the link is confirmed, it will be working like a standard TCP. Okay, so once the link, everything is confirmed, it will be checking and also it uh, checks with the low window size. Okay, so low window threshold value will be checked. Okay, so then it switches transition will be there. Okay, so more aggressive, it becomes more aggressive and it tries to increase the transmission rate. Okay, which will be guided by high window size. Until high window size reaches, aggressive growth will happen. So this aggressive growth will be checked with the high P value. Okay, to maximize the throughput without causing the congestion, this value will be checked with the high window size. So this is how the high TCP will work. So it starts like a standard TCP. So it checks with the low window size threshold value. So until it reaches there, the same it will not grow. Once the it reaches to low window threshold, the link will be once the link everything is confirmed, the transition will happen. It will grow, the window size will grow aggressively until it reaches the high window size. Again, this high window size will be increased in an aggressive way by checking with the IP value. in order to avoid the congestion. Okay, so this is how the high-speed recipe works. Right? Any doubts? Any doubts? Okay, now we see the quality of service. Okay, provided on the internet. So how the quality of service is provided in the transport link, right? So quality of service, the packet switch networks. For many years, the packet switch networks, uh, it supports multimedia applications like audio, video, data. Uh, Everything can be streamed. Okay, so once audio, video are digitized, they can be transmitted like data in the form of packets over the network, right? That is very easy. So the major obstacle here is in order to have the higher bandwidth things. Okay, so audio and video streams, they need high quality news, right? They require a large amount of data to be transmitted continuously without any interruption. So they require higher bandwidth news. So in early days, there was a challenge because the network infrastructure could not provide the required bandwidth. Okay, but in recent advancements, these limitations can be overcome. So implements are given for audio, video, comparison techniques. So we can reduce the bandwidth requirements for multimedia applications. Okay, so modern coding methods. You can have advanced video, advanced codes. Okay, all these allows high quality video to be transmitted like a much lower with the help of a much lower rate when compared to the older technologies. Right? So at the same time, the link speeds in a packet switch network, they have increased, right? So high speed bandwidths, like you can use the fiber optic cables. Okay. So advanced wireless networks, everything can be used to deliver the high real-time multimedia content in an effective way. So these two factors can be combined here. So in order to provide a better utilization in a faster network, you can use a higher bandwidth links. Okay, uh, long promised multimedia can be transmitted. That is real time data. The objective is to transmit a long audio video files or a multimedia files over my packet switch networks. Practically now it becomes reality. Okay, so timeline and timeliness and real time applications. While you provide sufficient bandwidth, again, there is a problem in transmitting audio and video over the network. So it is not only the requirement. So multimedia communications, they require interactive applications. So it demands, they require high data rates. We'll take a telephone conversation as an example. The participants, they expect to communicate naturally, right? So where one person will be asking one question, so another person has to respond to a to the question. So if there is a noticeable delay, even just a second or two, the conversation becomes very awkward, right? So it will be very difficult to maintain. So this brings us the importance of timeliness in the delivery. It's not enough for the data to simply reach its destination, but it must do within a time frame. So we have to maintain the natural flow of communication. So this is important in applications like video conferencing, online gaming, telemedicine. Okay, so those type of applications. They are highly sensitive to timeliness of data that are in real-time applications. So in this cases, predictably, predictable low latency data delivery, it is required. So together with that, it should give higher bandwidth, right? So quality of service, when we think about applications that require timely data delivery, voice and video are the examples, the best examples, right? Video conferencing, even our live lectures, voice over IP calls, okay, that you do on a WhatsApp call. So they have to maintain a smooth interaction. So the real-time requirements, they go beyond multimedia, okay? So imagine you have a robotic arm. Okay, so if there is a command given, stop or change the moment. Okay, so when that is being delayed, what will happen? The arm will crash into a machinery, or even it will damage certain systems, right? So certain machineries. So even a fraction of delay will cause a bigger problem. Okay, so even non-real-time applications like file transfer, they can have timeliness constraints. So in business that needs its database updated, that should be updated overnight. Okay, so the data transfer is not completed by the next morning. Again, it can disturb the entire operational team, right? So, but uh, the real time is not only with multimedia, but even for files, we have to provide timeliness is required. Okay, the guaranteed of you have to guarantee the service, right? So real-time applications and quality of service, uh, it sets real-time applications apart from traditional applications. So you have to assure the assurance must come from the network itself. Okay, the network should be able to guarantee some levels of timeliness. So non-real-time applications, they can give certain thing to use retransmissions to ensure accuracy. They cannot rely on such strategies, right? Real-time applications. For example, if a video frame or if I'm sending a voice packet, if that is being delayed or if it has to be retransmitted, so still, even if it is arriving correctly, but there is no longer, it is useful because it is based upon a time constraint. So all these things need timeliness that should be maintained. So in a real-time scenario, some packets should be given higher priority than others. So there should be a departure. It should guarantee that the destination has reached the packet, right? So real-time applications work by continuously capturing and transmitting and playing back data with a strict time constraints. Okay, so the first data will be generated, fine, by collecting samples from microphones or input devices. These samples will be digitized. Okay. Then you have to convert that into analog to digital conversion is required. Okay, so once it is digital, for digitalizing, we have to convert from analog to digital. So once it is digitalized, these samples can be packaged into packets. Okay, and it can be transmitted across the network to the receiving end. So the transmission must be efficient and also timely to ensure the audio video maintains the quality and synchronization. At the receiving end, the data must be played back at the correct rate. So if the playback does not match the original timing, again, distortions, the delays, there will be gap in the audio, video, everything. There will be a problem, right? So the real-time applications, the systems, they need timely delivery of data. So the common example here are the voice communication. If we take voice sample collection and playback, where the voice samples are collected for every 125 microseconds. So a new sample will be generated after 8,000 times per second. So in order to maintain the natural flow of conversation, all these samples must be played back at the same rate, that is 125 microseconds, okay, at the receiving end. So every voice can sample can be thought like a playback time will be there. So exact moment it should be cured at the receiving end. Okay, after 125 microseconds. So this playback time assigns with the sampling rate. So it has to ensure the smooth audio stream. Okay, so what is the timing with the receiving host? So the point is that the sample must arrive at the receiving host before it's scheduled playback. So if it receives or if it arrives too early, it cannot be buffered. Okay, so if it arrives late, the playback window will be paused. So both the way it will be useless. Okay, so one sample, if it is scheduled for playback at, say, for example, if I'm taking, uh, but it is arriving at 1, 1:30. So as we can see here, 5 minutes late, right? 5 microseconds, which is late. So even such a small delay can accumulate and it will affect the quality of communication. Okay, so this has to be, uh, these things must be avoided while you care your quality of service. Right? So the next one, the importance of timing in audio applications. In real-time audio applications, timing is everything, right? So there are strict limits on how much we can delay the playback of the audio data without affecting the user experience. So you're speaking to someone, okay, over the call. If there is a delay more than 300 milliseconds, okay, what will happen when you speak and when another person hears you? The conversation after every 300 milliseconds, the conversation is happening. So it becomes unnatural, right? So this threshold, 300 milliseconds, you have to consider this as an upper limit for acceptable delay in the real-time communication. So for the smooth communication, we have to guarantee from the network that all the audio packets will arrive within 300 milliseconds window size. So if the packet takes longer, there is a gap can be notified. So this has to be uh, properly handled. Okay, so the data arrives early. So that should be placed in the buffer. Okay, so we buffer it temporarily, so we can hold it until the correct playback time arrives. And then this buffering helps smooth the uh, variations in the delivery. Okay, so before the playback time, even getting the packets, all these things can be buffered. Okay, in order to maintain real-time interactions, you can make use of buffers as well. Okay, for providing the quality of service guarantee. So this is the visual representation of how the data packets are arriving in real-time applications from the generation to the playback. You'll see this is the packet generation. Okay, this line indicates the packets are generated. Okay, so when the sender creates and transfer the packets, the live audio streaming is happening every few seconds. Okay, uh, this is the network table. Okay, so the packet travels across the network. There will be variation, right? Varying amount of delay due to congestion, routing, other factors. The packets will be queued, right? So the packets will be delayed. Okay, so this line indicates the fluctuation in the packet arrival. So this is where the packet is arriving. Okay, so this is the fluctuation due to certain things. Okay, so in the network, the packet is arriving. The packet is sent. This is the network delay. So where the packets are arrived. Okay, so as you can see here, everything. This is what the packet is generated. This is how it should be played back. But there is a fluctuation here. I cannot play back in the same way. So what we can do, we can buffer the packets. Okay, so this buffering, the buffers can be used at the receiver side. So it can temporarily hold the incoming packet. So once all the packets are, if there is a delay variation, you can hold the packets. So after a certain time, we can play back so that the whatever that is being generated, you can hear at the receiving end. A smooth communication will happen. Playback time. In order to maintain that, it can be buffered and the receiving end can, the entire uh, voice can be heard at the destination side. Okay, any doubts? Any doubts, ma'am? Any doubts? Are you there in the meeting? Do you have any doubts? Rest of the topics we can see in the next class. So certain topics are there. The Q quiz will be enabled at 12:10. Complete the quiz. Let me know whether you can access the quiz. Kindly confirm whether you can access the quiz. Now, can you access the quiz? Kindly please confirm. Students, please check it out and let me know whether you can access the quiz.
Yes, ma'am, able to access.
Complete them. Can I complete the quiz? Post it in the chat box and then leave the meeting. No, I'll end the meeting. Make sure you're completing the quiz. Okay. Thank you.